A little bit of a warm-up here by asking the last question. Rick Elphic, who's going to talk on near-term instrumentation for landed lunar missions. What I'd like for this session is for everyone to limit their talks to 15 minutes, and then we're going to do another.
Oh, now you're telling me.
Then we're going to do another panel at the end. Thank you.
Okay, so you see Sam Lawrence's name on there, and that's because this is basically a slide package that comes from one of the special action teams, the specific action teams that League commissioned. You heard from Brett Denevi earlier today about one of those, the ARM SAT, and this is from the next SAT where we discussed basically the next steps or the next missions that might go to the surface of the moon and carry out, or even an orbit around the moon. So that's where this is coming from. If you like it, it's all to the credit of Sam Lawrence and the team. Is this supposed to be a pointer? I'm just curious about that. Oh, cool. Look at that. Little green ball. Okay, and then in ugly mustard-colored text, that's stuff that I've put in that doesn't necessarily reflect the team's input. So the Special Action Team charter in this case, which is going to lead us eventually to instrumentation, so this really will hit that point, basically starts off with new lunar science questions that have been raised on the basis of sample studies that have been conducted since Apollo, and more importantly, perhaps, the most recent LADEE, GRAIL, and LRO mission results, which really have transformed our knowledge of this, the state of the surface of the moon and the interior of the moon. So what we've been charged to do in this SAT is determine desirable precursor instruments and/or missions to enhance human exploration and to address the SKGs that you heard about earlier. But also, and this is a really exciting part of this and part of what has led up to this point in our discussions this morning, involvement of the commercial sector, the private sector, carrying missions to the moon, carrying payloads to the moon, landing them on the surface, whether they're from NASA or NASA-sponsored or by other commercial entities out in the world. It really opens the door to, and in the near term, presumably, to a lot of possibilities for returning data from the moon. And these other things I'm not going to talk about today because my charter was actually to look at instrumentation. Here's the cast of characters, illustrious folks, except for people like Elphic over here, but you know these other guys are respectable. So you can trust a lot of what is being presented here. We understood right from the get-go that if you put humans on the surface of the moon, that's tremendously enabling. You give them equipment, you put them on the surface of the moon, and you can get a lot done. A lot more done, in fact, in terms of traverse distance and in the depth of the science that's done than is in many cases possible with robotic missions, especially short-term one. And a second thing that was part of the constraints that we were working under was the fact that we needed to consider the missions and instrumentation that would be carried out in the next 5 years or so. So fairly short term. That's pretty short term compared to like a large NASA mission to the outer planets or something. We didn't really go into cost estimation because that's always dangerous ground to be on. We always lowball things as scientists and some of us as engineers, and it always ends up being a higher costing in the end. So we thought it was just better stay away from it and just categorize these things according to small, middle, and then large. Okay, so the primary finding was that there's a lot of science questions. There are basically a lot of the twists on old questions. A lot of the information that's flowed in from recent missions and from some sample studies are similar to things we've asked in the SCEM report. And that's why you heard Brett say earlier today that basically the SCEM report is still germane, and a lot of the details and questions are actually multiplied because of what we've learned from the missions. So for instance, absolute ages for the geologic units, the time and stratigraphy relationships between basin-forming impacts, characterizing the lunar volatile content, that's always been there. Structure of the lunar interior, we've really needed a geophysical network on the moon for a long, long time. Understanding magnetic anomalies, where they come from. What does it say about the dipole that once may have existed on the moon and is now shut down? Or is it from another source? Lunar volcanic processes, we now know there's a bunch of different eruption styles, lithologies, and obviously histories and locations and the relationships in time through all those things, which speak to the thermal evolution of the moon. And then finally, the resource potential, which is really interesting because if the moon turns into a gateway for exploration of the rest of the solar system by using its in situ resources, that really is a game changer, obviously, as everybody knows. We won't be talking about orbital missions, but in this case, I'll be just focusing on sample return, rovers, and stationary landers and what you can do with those. So here's another finding. Commercial opportunities are really, really, really important. I'm just speaking to the choir here, I know, because everybody has been talking about that this morning and in recent months. So the Commercial Advisory Board meeting that was referenced here basically identified and recommended to NASA that it should strongly consider buying transportation services, even buying samples from sample return missions and or data from missions that are carried out at the moon from commercial entities or carried out or enabled by commercial entities. So right now, HEO-MD on behalf of both SMD and STMD is about to release, I don't want to say too much, but they're basically getting ready to release opportunities for folks to respond, for the commercial entities to respond and actually come up with ways of getting us to the surface of the moon in partnership. So that's part of that public-private partnership. Okay, so what we're looking in the future for then, for all missions and instruments to the surface of the moon are these surface delivery services. Folks that have talked this morning have told you about the plans that they have for landing on the surface of the moon, some of them hopping to different locations on the moon, some of them doing sample return. And so already these things, even though they're computer-generated things, they look very, very promising for the future of science. Okay, so missions addressing key questions. This is just a list of kind of a little bit like motherhood questions. Fixed and stationary landers, two examples of that would be the Lunar Geophysical Network. ILN has already been studied and gotten very mature, so we know we ought to be able to do something like that, and that also can involve international partners as well. But if the platforms are provided near term by commercial entities, then that's a good thing, right? Something that people haven't talked about too much is the plasma and electrical environment of the lunar poles. There's some concern about that. Personally, I'm not concerned about it, but I can see where the arguments come from. That charging is differential charging may be important up there, and the charging of dust and lofting of dust may be important. Mobility-enabled missions are huge, right? That they basically give you the opportunity to traverse across magnetic anomalies, to understand volcanic processes by carrying out traverses and exploration through complex terrains, such as the silicic features like the Marius Hills, through stratigraphic sequences of Mare basalts, like at Hadley Road would be exposed, and so on. Resource potential of the lunar poles, again, motherhood. I mean, this is really, really important. We don't really know enough about those things to make any reasonable decisions about the future progress of space exploration through the solar system. It's important to recognize that not only permanently shadowed regions, but also subsurface cold traps. As I was saying to James earlier, there are locations where the ice could be stable if it's present within a few tens of centimeters of the surface, and these are locations that are occasionally sunlit. So you don't necessarily have to operate in darkness and in cold at the surface. Just below your feet, a few tens of centimeters down, it's going to be cryogenic. That's just the virtue of the lunar regolith. So these other things are things that we've already talked about, and Brett presented very nicely for the SCAM report. Basically, bulk chemistry, the geology of lunar pyroclastic deposits, whether these are resource potential or not, almost certainly they are. History of lunar volcanism, absolute ages of basalt units, tectonic processes. We could take traverses over thrust faults and understand what's going on in the subsurface and better understand the shrinking of the moon. Lava tubes, just to give Junichi-san a little bit of time here. It's obviously pits and lava tubes are of very great importance to us, especially in understanding stratigraphy. Basin formation, ages and stuff, this is just all the same thing that we've always talked about that's really, really important to do and could be done. Sample return missions, at least one of the commercial entities talked about doing sample return this morning. So that's very cross-cutting. It goes across all these different science questions, and so it's really a hugely enabling capability if we can make it work. And sooner is better than later, obviously. So the missions that we're talking about here, as I said earlier, to accomplish these things would be the SAT decided that they would divide the groups of possible missions into these four: orbiters and small landers and stuff. I'm not talking about orbiters, even though there's a lot of things that can be done by orbit. A lot of them are in work now on CubeSats. But small landers would be carrying less than 40 kilograms to the surface. Larger landers and possibly carrying rovers would be the 40 to 500 kilograms. Really no upper limit on that if you can provide it to the surface. And then sample return missions are a whole different level of complexity, as Brad Jolliffe will tell you. So basically dividing these things up into three. Let's start off with 5 kind of representative mission scenarios. One is to understand irregular Mare patches. These are putatively very young basaltic volcanism settings, although there's controversy with that. They could also be very, very old but frothy and hence beaten down. They look young, but they're not really young, according to Jim Head. So by doing a small lander to the surface, 40 kilograms of payload could include things like, and with no night survival, could include things like descent imaging, major element chemistry, macro and micro scale imaging, in situ geochronology, which is important to establish the age of the formation that you're looking at. But you also need to acquire, in order to do that, you need a sample acquisition system. And so this is a thread that'll run through a lot of the landed discussion. Once you've got more capability, 40 to 500 kilograms or so of payload to the surface, and mobility, and the ability to survive the night, then you can actually go to any of these locations and really thoroughly explore all the lithologies, the geochemistry, and the textures in all these different locations. So it's hugely enabling to do that. Sample return, obviously, if you go and grab it and bring it back to the Earth, then you enable all the things that Chip Shearer was telling us about earlier today, which is really a gift that keeps on giving, of course. I'm not going to talk about desired technology investments, but we can later on during questions if you want. Magnetic anomalies, really mysterious things on the surface of the moon. Swirls are related to them. And so if you take a package to the surface, thing that would make sense to, at the surface, and as you could do in a 2-week interval during the day, is imaging and in situ measurements of the surface vector magnetic fields. That actually was done already on Apollo, but not with the coordination that you would need here. You'd bring along plasma instrumentation and radiation environment monitoring for the swirls areas to see if the solar wind really is responsible for preserving some locations or maturing some locations and shielding others. If you carry out a mission that has more landed capability along with mobility, you could actually carry out traverses across the swirls and across the magnetic anomalies and maybe be able to map out in detail what the high multiple order structure is of the magnetic field and get at what the magnetization has to be in the subsurface and basically identify what the source of the magnetization is. For sample return, it would make sense perhaps to bring back samples of this magnetic material just to give, I won't say any more thing about that because I don't think that case has that much going for it. Structure of the lunar interior. This is obviously really important for geophysical networks to be able to basically perform seismic studies and to be able to do heat flow, to be able to emplace retroreflectors so that you can do the long-term variations, lunar configuration. Once you get into a lander with mobility and night survival, this is now a point where you begin to be able to not only emplace fixed instrumentation such as seismometers and heat flow probes, but also be able to do sounding from different locations, and you can even imagine doing gravimetry across a transect, in this case to understand what you see in the subsurface. Sample return obviously would be really great along the lines of the South Pole Aiken sample return to return mantle material in order to characterize the composition of the mantle. The fourth example is polar volatiles, my favorite, to get at the composition and physical state. Basically, you can land in the darkness and carry out something like a landing site in Cabeas, for instance, where L-Cross showed that there's water. Basically take imagery of the interior of the the PSR with the lighting that you carry with you. Identify superficial ice composition, obtain a subsurface sample, which again requires subsurface access and sample handling. So we can also determine the volatile abundance, and with a gas chromatograph and mass spectrometer be able to do chemistry and isotopics. Once you've got more mass to the surface and mobility, you might want nighttime survival and out-of-com capability, because the Earth may go below the surface, as we know with Resource Prospector. But again, you can do the same things as you were doing here, but now you can do it from a variety of locations. And one of the things that I wanted, again, to point out is that you need to measure the subsurface concentration of volatiles continuously, not just at multiple stations. In other words, not poking holes randomly around, but just to be able to do it with guidance and with understanding what is in the subsurface based on what you measure as you rove. And of course, as we've talked about in previous talks, sample return is really important for this. If you can get the volatile bearing materials back in pristine condition from multiple locations. Bombardment history of the inner solar system. Again, if you go to the surface and spend 2 weeks there, you'd want to take descent imaging, surface operations imaging, major element chemistry, if you can, and obviously acquiring a sample to do that, and in situ geochronology. Here, the idea would be to carry on a small lander, on a series of small landers, carry the same instrumentation that allows you to do the geochronology, for instance, at multiple locations, and thereby get a handle on the geochronology of the moon. But of course, once you've got to mobility and nighttime survival and out-of-com capability, the sky's the limit, because you can wander around and pick multiple sites to do this kind of thing with. Sample return, obviously, that's been argued for and is clearly the way to go if you really want to get that gift that keeps on giving. So here's my list of instruments for near-term lunar surface missions. They include things like a sample acquisition and handling system, a surface contact system if you're going to take something along that just simply measures the composition with a contact instrument such as APXS. Major element chemistry, geochemistry can be done with the usual suspects, APXS for contact. Remote sensing, LIBS will work. We see it working on MSL. Gamma ray and neutron spectroscopy also works for the local region that you happen to be roving over. For mineralogy, the tried and true methods of near-infrared spectroscopy, and for sample analysis, XRD, XRF, Raman, so on. You'd want to carry imaging capabilities with you. You need, and I would argue you need in situ isotope geochronology again, a mass spec, and volatiles analysis. For GC and mass spec, this is what we'd be doing this is what we are doing on Resource Prospector. So for, again, these stationary landers, seismic for the geophysical network, heat flow measurements, retroreflectors, and if you're doing the interior, analyzing the interior, plasma particle, electric fields, and so forth, and electromagnetic sounder. All the above for a mobility system, of course, that's a no-brainer. In addition, you might have gravimetry and ground-penetrating radar for the geophysics as you rove around. For prospecting tools in the volatiles case, if you're at the poles, or well, mainly at the poles, you'd want to take imaging, a neutron spectrometer, LIBS, near-IR spec, GPR, and so forth, or some subset of these things in order to allow you to evaluate the data as you prospect, as you drive around. One of the things that it seems to me is kind of important is to keep in mind this 5-year horizon and what that means for instrument maturity. So if you had a commercial provider that said, I can accommodate you 365 days from now, we have an ICD in place and you guys just need to meet that ICD. Can we make lunar surface access through this mechanism affordable enough to fly things like engineering models or even qualified COTS payloads? Is it cheap enough that we can take that risk so that we get cost and science benefit at some acceptable level of risk? That's something that NASA needs to decide if they will support it. But you can imagine that there may be entrepreneurs out there who are willing to take that chance. So that's a question for the community. All right, I'm sorry, I'm done.
Thanks, Rick. Yeah, we're going to do that, yeah. Okay, so we're going to wait for questions until the panel at the end of this session. So our next speaker is John Gruener, who's going to be giving his presentation remotely. And for the IT folks in the back, is John online now? It looks like he is. Hey, John. Can you hear me? All right, I'll let our IT group resolve this. John, if you can hear me, we cannot hear you.
I still can't hear anything coming my way. Can you hear me?
Yeah, we can now, yeah. If we could turn that up a little bit, please.
All right, so I thought I saw Greg shake his head up and down.
Yeah, we can hear you now. Go ahead, John. Thank you.
Okay, so I can just go ahead and start my talk, Ricky, even though I can't hear what Greg is saying at the microphone. Give me a thumbs up if that's a good idea. All right, then. So you just heard a talk from Rick about a league-specific action team in the summer, and then also Brett earlier in the day. We have to turn our Wayback Machine back about 9 years to talk about another specific action team that worked with us in Constellation to develop a set of regions of interest for looking at spots on the moon and where we would want to take images with LROC. It's really hard for me to remember a time before LRO because we you know, and Selene and all those other great missions, but that's where we were at the beginning of Constellation. And so I'm going to remind everybody the process we went through to come up with our regions of interest and why we chose that term regions of interest instead of landing sites. So I'll go here to the next slide. So Ricky, I'm clicking on the little button. I just got to pick the right button. Okay, so here's just a quick summary of my talk, all on one slide, in case you have to get up, go to the bathroom, or get something to eat. So the Constellation Program Office worked with Mark Robinson and his LROC team to come up with this operational approach of regions of interest. And it was really critical working with Mark because he knew you know, what his instrument could do and how best to use it. And so a lot of the recommendations he gave us, we just took and said, that sounds like a great idea. So we decided on 50 would be a reasonable number that we could image in the first year, which was the HEOND part of the mission, and that we would divide those 50 sites into 2 tiers, where the first tier would have higher priority than the second tier. And each one of those regions of interest would be a set of nested boxes, if you will, where the middle of the box got the most imaging and stereo, and as you got further and further out away from a point, they just, you know, they would do their best effort to get what they could for us throughout the mission, because they had their own high-level requirements as well. So once we had an operational approach, then we had to come up with a list of 50, all right? And we basically did that by using the Lunar Science Community's documents and papers, and also the papers out of the Lunar Resource Utilization, because as you'll see in the slide, you know, this wasn't all science. These 50 regions of interest wasn't all science. It was a mix of things, right? So once we, within Constellation, came up with our 50, we requested a league team to look it over, to make sure that we did our homework right and chose some reasonable areas. And the league sat came back. I guess we got about a B or maybe a B plus because they didn't really change a lot. Didn't kick out too many of ours. And we finalized a set of 50 regions of interest, and then the LROC team did their job, and they really did a great job because all those sites were covered very, very well. All right, so when we talked about these way back when, we had to emphasize that these regions of interest are not landing sites. All right, it was the first step in trying to figure out where we might go, once we had the data to tell us what the sites were like. And it wasn't just science. We were looking at science, we were looking at resources, but we were also looking at terrains. You know, earlier today you heard about different types of terrains because we were going to have to operate in those terrains with spacesuits and with rovers and such. So we wanted to scope the problem in three different ways there to get a set that kind of form a representative basis of everything we might want to do on the moon in the way of mission operations. So here's how the regions of interest came about. Again, Mark Robinson played a key role in this, where we settled on the number 50, divided up into two tiers of 25, where the first tier had more priority than the second tier. You can kind of see that there in priority 1, 2, 3, and 4. And the 10 kilometer by 10 kilometer box in the middle would get what we call full observations. And there you can see a list of everything that would be considered a full set of operations. And it's quite extensive. And one of the reasons from Constellation that we were interested in this full set, of course, is because we wanted to land on the moon. And we would like to know things like slope and rock abundance and roughness and all that for our landings. So many times our 10 by 10 kilometer box was rather conservative. We always tried to keep, you know, some flat area within that box, and sometimes maybe we did that a little too much. A little later you'll see the Gratoisin Domes is one of our sites. You know, we didn't have enough of the slope of the domes in our 10 kilometer box, so during the mission, working with Mark and his team, we said, yeah, go ahead and move that box. We didn't really plan that one too well. But that was, the 10 by 10 was where we were hoping to land. And then with rovers, of course, you can get further and further out. So we had our 20 by 20 box and then our 40 by 40 box, where we would do, the best effort competing with the other priorities of the mission. All right. So once we had an idea, we had 50, and then we had an idea of how we were going to set that up with the nested boxes. We had to, fill out the list of what 50 we would use. And, it made sense to use the decades of work that had gone on before, not only in the lunar science community, but in the lunar resource community and also in the NASA planning community. If you remember, this mission was under Bush II with his vision for space exploration, but under Bush I, we had the Lunar Outpost with the Space Exploration Initiative. And the science community had come up with sites that they thought were good for a lunar outpost. So we included those sites. And then the ISRU, and you can see the small list, the small group of people that got the list of 50 together initially. And then within Constellation, our customers were really the lander people, the Altair people, and the ALHAT, which was the lander hazard avoidance people, because they needed to land there. And then, of course, the office that I worked in, the surface systems, where people were talking about rovers and spacesuits and habitats. Those were our two main customers within Constellation for these regions of interest and getting this data for the regions of interest. And like I said, this was pre-LRO, so the data sets that we were relying on to even identify the ROI, go all the way back to the lunar orbiter images, because some of those were quite good and quite high resolution. But also all the instruments in the Apollo scientific instrument module, particularly the metric cameras. Clementine had flown, and we started getting our first global data sets. Lunar Prospector followed that, and again, more global data sets, and particularly the whole idea of water ice at the pole started really coming to the fore, flying in this time frame. Selene, Chandrayaan-1, and Smart-1, their data sets were just starting to come out into the science world and at LPSCs, and people were just starting to use those data sets, but we weren't inside of Constellation. So we came up with a group of 50. and you'll see those in a bit. And then ask League to check. It's called the LROC SAT, and you can find the report at the League website, along with all the League SAT reports. And you can see they broke it up into 3 groups of science and then an operations subgroup to match what Constellation was trying to do, set of ROI. And Paul and his gang developed a scoring system to see how these things rate against each other and how they just rate in general. And they went through their system, and they came out with sheets kind of like this to give the scores. I forget why these 3 were highlighted, but that's not really important for this chart. The chart is just to give you an idea of how the 3 different groups, science, ISU, and ops, went through and scored the groups and then rated the groups. And then this was their summary, or this is what came out of their report. So 45 of the 50 that we had picked pretty much remained the same. They did shuffle a bunch of those around between Tier 1 and Tier 2 because some that we thought might have high priority were different from the ones they thought had higher. They moved 2 of our regions of interest. They liked the regions of interest generally, but they moved them to a different set of coordinates. They asked that a couple of ours to be deleted and replace them with 2 others. And pretty much everything League said we accepted because those guys were the experts after all. Right? And so then we came up with the finalized list and published the list. And this is a list of the Tier 1. Now, as I understand it, all these presentations will be available PDF after this workshop. So I'm not certainly going to go through all these, but you can look at them later. And there were Tier 2. Excuse me, and you can see INA was one of them. That was kind of fun hearing those talks today about INA. All right, and so Ben showed this map earlier. You can see we tried to cover the near side, the far side, the poles, Mare, Highlands, to get a broad scope of the moon. Again, within Constellation, we were doing this to check that we had the different areas covered by all the different sites. This is the Tier 1. Here are the Tier 2. You notice at the very bottom the anomalies. So things like Compton Belkovich and Reiner Gamma and INA, all these really cool things that you've heard about today. We refer to them as anomalies, and they were all in the Tier 2 bunch. But all 50 of these got covered very, very well. Now, as you all know, the sad history of Constellation, it was canceled. And but LRO kept working along, and we had Wendell Mendel, who was the leader of our Lunar Planetary Exploration Office. We were coming up with a way to convince ourselves that yes, we have all the data for this ROI that we had hoped to get, and then we can kind of close it out or move on. But before we got too far in the mission, things just kind of went belly up in Constellation. You can see we were doing things like this to make sure they are all getting covered. But again, the LROC team was just great, and all team members were given different Constellation regions of interest to follow to make sure that they were getting what they promised NASA, and it all just worked out really, really well. All right, so that's about it. These Constellation regions of interest still live out there on the internet. These are all links that you can go to if you download the PDF. They should be hot linked, or you can go to the abstract that kind of describes what I went through. You can get the League SAT report, the 2 different Tier 1 and Tier 2s. And then earlier today, Noah Petro mentioned QuickMap as his favorite thing to go to. That's a great place to go to see these regions of interest and see how well they are covered. The CX Targets is one of the overlays in the layer section off to the left, when you're adding different layers, when you go into Quick Map, the CX targets are one of those. And then when you put the NAC footprints on them, you can see that they're all very well covered. And I'm thinking that's about it, Greg and Ricky.
Okay.
I don't know how I'll answer questions since I can't hear anything.
John, thank you very much. Can you hear me now? Can you hear me? Evidently not. Ricky and Ashcon, maybe you guys could call John and we could get him on. Yeah, and Yvonne is giving a thumbs up to that. So great. And if you could please ask him to stay until after David Kring's presentation, when we'll take a few questions. So thanks again. Our next speaker is Tony Colaprete, and Tony's going to be talking about Resource Prospector, about mission goals and landing site constraints.
Thank you, sir.
Thank you. 15 minutes.
Okay. Good afternoon. Hopefully some of you will see something new. I've presented similar stuff at League and AGU, but I did try to make today's presentation much less of the project overview and where we're at programmatically, technology and stuff, and much more about landing site selection, the process, new data sets, some of which will be made, start to be made publicly available, new processing techniques, et cetera, for getting new data, working with the data sets that I think are very relevant to these questions. So let's see if I can go forward with this. Ooh, wrong one. All right, so real quick, one slide, RP, why RP? To beat the dead horse some more, we're really interested in understanding lunar volatiles as a resource, particular polar volatiles. The exploration roadmap, global exploration roadmap, calls us out specifically following the number of missions who have identified this potential. RP was born out of that to really understand better at the scales we need to operate, the human scale I call it, the distribution, forms, accessibility, et cetera, for resources. And it really is all about addressing the ISRU potential at the poles. And there's a wide range of possible resources on the moon. Polar volatiles is one of them. RP's focused on that. It's not to say anything about the others being better or worse. It's just we need more information to assess this as a resource, and that's what RP is all about. And this is not new science, not new exploration. We do this on Earth all the time, and RP borrows very heavily from our terrestrial counterparts who do exploration on Earth for resources. And for example, this particular figure here shows RP's role in a traditional mining resource characterization flow path, where we are trying to understand the mineral reserves, if you will, of the lunar polar volatiles. And that's important for really understanding the viability and the economics. It comes down to return on investment. Is it available in a way that is actually fundamentally enabling of architectures, or actually in a way that is economically beneficial to governments or commercial partners? So with this in mind, RP is formulated differently than a traditional science mission. That said, science is inherent in exploration and vice versa, so you get great science from it as well. So the first part of any exploration assessment in terms of a resource, it's the ore grade or the reserves of that resource, if you will, is to understand the distribution, and really it comes down to the prospecting. We've been doing this for hundreds of years on Earth, thousands of years really, and we can take those things that we know how to do and apply them to how we're doing them on the moon. And so really the first step is to provide the strategic knowledge input for this potential. What are the location and the environments of these potential resources where the return is at a maximum? And it's important, we've heard this today, it's not just about concentration, it's about accessibility, it's about the environment you're working in. All those things fold into the accessibility and the return on the investment. And that's what RP is really all about, not just getting at what is the water concentration. And in doing so, also then, we need to bridge the gap between what we see on the surface, what we see in orbit to make these assessments. So we need to understand what that ground truth is, the linkage, as I just mentioned, between the on-site conditions and orbit. Woo! How do I go back? Okay, I'm going forward. Stand by. There we go. And also, lastly, test theories of emplacement and retention. So we need to understand how it got there, why it's there, and so we can better assess from global maps, if you will, or regional maps, what that potential is. So we can't just go and stick a drill in one place and understand things. We need to understand it much more regionally so we can extrapolate to the bigger problem. There's other reasons there are other motivations for having mobility too, and that's key for Resource Prospector. You heard about stationary landers and mobile platforms. We really think that for understanding resource potential at the poles, mobility is key. You will not be able to do it well or at all with a static lander, and that's because the things that dominate potential resource localization are mixed at very fine scales down to meters perhaps. And this is because we think, at least right now, based on what we understand, is that crater mixing is one of the dominant geological processes that's mixing the top meters of regolith. And these are some simulations down here from Dana Hurley et al. That shows that over time, if you had a patch of ice, it's going to get broken up. It's going to look like more and more like Swiss cheese. That's kind of intuitive and obvious. And you can actually understand what the potential mixing scales are based on craters of 10 to 5 meters or so in diameter, that you expect this kind of mixing to occur at tens to hundreds of meters. So it's a pretty small scale. It's hard to understand that from a neutron spectrometer in orbit. Good luck. We've got a footprint of tens of kilometers, let alone hundreds of meters. Likewise, in temperature control, we know is important. To have water stable, you need cold temperatures. That said, we also understand that just being cold is not enough to have water. And that we don't quite understand. That's one of the more perplexing aspects of the lunar poles and volatiles is right when you think you're looking someplace you'd see water frost, you don't, and then you see it over. It's not making much sense to us. It's not behaving like Mercury, which is well behaved. And we do know that these variations are largely determined by topography on the moon. And those topographical variations, those scales are very small, down to less than 5 meters. So you can have temperatures swinging 100 degrees in 5 or 10 meters. That could be very important for the scale at which we're working, distribution of water. So this kind of argument is what's really driven the motivation, or it's motivated the need for mobility, the scales of which we need to sample across, and the resolution at which we need to sample. Oh, and this is one map down here showing ice stability. Rick Elphic mentioned this in the question session a little bit ago. This is from Matt Siegler, more recent work, down to where we're calculating the ice stability depth at 20-meter scales now to really look at this. So along these lines, to evaluate the resource potential, and again, it's not just trying to find the wettest spot. That's not how you actually want to assess and understand what is the potential resource reserve. We need to understand the distribution of volatiles across a range of regions. And so we do this by identifying potential regions in 4 different types of environments that we define using temperature. We basically define dry, deep, shallow, and surface temperature regimes, meaning dry is where temperatures in the top meter are expected to be too warm for any ice. Deep means between 50 and 100 centimeters we expect water ice to be stable. Shallow, it's more near the surface within the top 50 centimeters. And then surface, it's stable at the surface. So in a permanently shadowed region, for example. And so we can take Matt Siegler's work here, which gives us the depth to stable ice temperatures, and then break that down into these kinds of maps, which is what we call a resource target region map that shows these 4 regions. And we can use this to develop schemes for actually visiting each of those regions and evaluating in a way to understand whether or not any one of these is more economical, safer, more beneficial than the other. But we want to do all of them, not just go to the wet place. We have to go to the dry place too and understand it. Last point on this, and then I'll move on to some site selection stuff, is we need to understand each one of those regions then, those 4 regions at the scales I was just describing in terms of temperature and cratering. This really does borrow heavily from terrestrial mining dialogue, if you will, or methodologies, as we need to first understand the fraction equivalent of the ore body. So on a scale of like 50 by 50 meters here, this area, we need to understand what is the average concentration here. So I can say if I got a dump truck full of this material, what's my average concentration? But then within that equivalent volume, we need to understand the variability, or what's often referred to as the delineation of the ore deposit. How is it distributed in there? That gets to how you're going to access it, how you're going to extract it, how you're going to work with it. And then lastly, we need to understand what's the variability from one of these equivalent volumes to the next. So if I found a great piece of real estate here, looks very promising, and it has these characteristics, thermally, for example, am I likely to see similar characteristics if I go to another one, say 100 meters away? And 100 meters was chosen because of that, again, cratering length scale. It has to be at least 100 meters away. Otherwise, you may be sampling just similar materials. So this, again, drives a lot of our traverse planning rules and sampling techniques and instrument footprints, et cetera, in terms of evaluating the overall ore potential. I was asked to say a little bit or trace to the SKGs. There it is. You can have these slides and take a look at them. This is a HEO mission. It's led through AES, the Advanced Exploration Office. Thanks for a minute, okay. And so we do obviously address the SKGs, in particular, the understanding of lunar resource potential. But we do all the others too. In understanding the lunar resource potential, you're working on the moon. But there's great science that comes out of it too. I'll go through these rather quickly so I can get on to some of the site selection work. We did do a trace between what RP is doing and what a previous mission concept, the Lunar Polar Volatile Explorer, is doing. And there's a great trace between the two. We do some very good science with the various instruments and measurement techniques and traverses that we have planned right now. But I'll leave that for you to read through later. Likewise, we trace very nicely to the SCAM report too, in terms of attacking a number of the high priority measurements that were described earlier today. Lastly, so landing site requirements. We are a cost-constrained mission, like all missions usually are, if you're unlucky, I guess. And so we have, from the onset, said we will not be nuclear or solar powered. Also, we will not need a relay satellite. We will use direct Earth communication. Immediately that, along with our level 1 requirement here in terms of landing location, immediately defined a Venn space here in this, or a space shown in this Venn diagram, where we could land. It has to have an overlap between where we think there's volatiles, where we can communicate with Earth, where there's sun illumination, and where there's traversable terrain. So we built a process over the last few years to really identify various sites and evaluate our engineering, our design, architecture, et cetera, against the various sites. And it starts at a high level. As you can see here, it starts at this kind of regional level where we identify places where we think there's volatiles. We take a look at the various environments there at a fairly large scale, both slow, static quantities and dynamic, which are critical. Here James mentioned that you're always chasing the sun. You are, and sometimes chasing the Earth. And then we boil that down into really targeted regions where we look at very high resolution DEMs, generate the same kind of products, slopes, calm, sun, et cetera, subsurface, temperature, stability maps, et cetera, and we then plan against those. And that's used to, one, evaluate the measurements, but against the requirements, but also help engineer the mission overall. Real quick, a few sites we've looked at in detail. These are study sites. Again, we have not picked a final site. We won't be doing that for some time by design, but these are sites we've used to, again, evaluate the tools, the products, and the inputs to the rover and operations development. We have 2 in the north and 2 in the south. This just kind of shows regionally where they're at. Again, they were driven mostly at this level by high hydrogen areas and obvious sun and calm places. I'm going to focus on one, Hermit A, which is right here, that shows the hydrogen abundance from Lunar Prospector neutron spectrometer. And this shows then some of the high resolution data products we're using in our planning. This shows the hydrogen ice stability maps that we have down to 20 meters, slopes that we have in some regions down to 1 meter with some new DEM work we have. And of course, then we have all the DTE and sun coverage that is a function of time. So you have to fold all this together in understanding the site and whether or not you can work at it. Now this goes for a static lander and a roving lander and everything else. So coming to my conclusion. So now one issue that we've come across is a problem, what I call a problem of scales. It's one thing to land, it's another thing to have a rover and operate on the moon. And if you talk to a designer and an operator of a rover, they want to know the situation at the scale of their rover wheels, which is, you know, in our case, it's 50 centimeter wheels. Well, that's a problem. There's no DEM at the 50 centimeter or 1 meter scale or anything like that. Stereo gave us maybe 3 to 5 meters or so, stereo. So we've internally funded Ross Beyer and his group to develop a photoclinometry or shape from shadows technique to get us DEMs at the scale, at the posting, native posting of the images. And this doesn't require stereo, it just requires lots of images with lighting in lots of different directions. And they've now validated it, it's working very well, they validated it against other models. And this shows an example in the, what we call North Nobile region. This is a 1 meter posting. You can see about a 10 or 15 meter boulder rolling down the hillside here. That's a DEM, so you can go in there and get elevations and everything else from it, and slopes. Likewise, working very closely with Matt Siegler, who's generating these awesome products, looking at ice stability maps at the 20 meter scale, and eventually we're going to go down to the 1 meter scale with these, again, using these DEMs. This takes, I think this took 10 days on a 200 CPU cluster down at UCLA, if I remember, something like that. Lots of computation. And then finally, we have these this really nice simulator that we've developed at Ames, which is, I don't know if I can get it to play. I don't have the control. Find enough control. Anyways, hey, I got it. Go. Cool. All right. So this is a simulator that goes down the centimeter scale that the rover team working with the science team has developed, and it takes in all the inputs we have, crater densities, rock densities for the polar regions, which are actually, we had to do a lot of groundwork for that, and then combines it with illumination models, textures, et cetera, and allows us then to actually test rover designs, driving it, et cetera. And this actually ingests the DEM, high resolution DEMs, thermal models, et cetera. So we can really plan this mission at a detail for any of the sites we're looking at. My last slide then is we've also looked at ways to more broadly examine and find these sites. This shows the Hermit A area again with some new automated traverse search tools that takes into account all of our requirements, everything from wheel slip to sun, calm, slopes, everything. It can go in there and identify clusters of traverses that satisfy all the requirements that are these white areas around Hermit A. This is the crater Hermit A. And you can go and zoom in on these, and now these are those 4 regions of study, and we can then automatically find traverses throughout those and look at across literally like thousands of traverses and statistically start to understand what are the conditions in any particular landing site. This helps us understand traverse robustness overall. And you know, those engineers, they like robustness and lots of margin and things like that. So that's it. Thank you. Yeah.
Thank you. I've seen a demo of that tool, and it is just fantastic. So our final talk of this session is by David Kring, Lunar Landing Sites, addressing NRC 2007 objectives for scientific exploration of the moon. Thank you.
Okay. This document's already been introduced today. It's a very robust document, but let me say a few more words about it. This is what I would refer to as the NRC 2007 document. I don't like that other acronym. And this was produced in 2007, and importantly, it identified 8 science concepts that Brett introduced, And within those concepts, it identified 35 specific investigations. And importantly, it prioritized at least the top of those investigations. This is what those science concepts are. We have bombardment history of the inner solar system, the structure and composition of the lunar interior, providing fundamental information about the evolution of a differentiated body. Key planetary processes are manifested in a diversity of lunar crustal rocks. The lunar poles are special environments that may bear witness to volatile flux, and so on and so forth. And I'm not going to read through all of them because Brett already did earlier today. But I am going to what we did several years ago was we used that document as a baseline or foundation for a global lunar landing site study. And so we took each one of those investigations and we asked a very simple question: where on the lunar surface could those concepts and specific investigations be addressed? And so this was not in a subjective environment. It wasn't like I did my PhD in Orientale, and so, my gosh, we have to go back to Orientale. You know, the idea was to actually take those investigations and identify every single place on the lunar surface you could address them, okay? So this generated a large number of global maps, and the idea would be that once you stack those maps, places that may not have occurred to you in the past as being incredibly scientifically rich would pop up and rise to the surface, and that is, in fact, what happened. Okay. So we actually did this over 6 years. We did this through NLSI and survey funds through summer intern programs. So these are 10-week programs over 6 years. These are all of the graduate students that participated in this. And some of these, this is a few years ago now, and some of these interns are now mid-career scientists. You heard Jessica Flout, for example, mentioned in James Carpenter's presentation a little bit a while ago. So these are really good people. And they did a phenomenal job with this project. We looked at concepts 1 through 7. We did not look at concept 8 because concept 8 was being addressed by Laddie. We did, however, ask a different question. NASA headquarters asked us to ask if we landed in only the South Pole Aiken Basin, how many of the investigations could you address? And I'll close with a comment about that. Okay, so I want to actually illustrate this process with concept 1 and concept 4 and then talk about the highest priority landing site. Concept 1 is the bombardment history. The inner solar system is uniquely revealed on the moon. Okay, so this is broken up into a series of investigations. Investigation number 1 is test the cataclysm hypothesis by determining the spacing and time of the creation of lunar basins. Number 2, anchor the early Earth-Moon impact flux curve by determining the age of the oldest basin, the SPA basin. C, establish a precise absolute chronology by measuring ages of representative craters throughout the moon's history. And 4, D, assess the recent impact flux. So each one of those investigations was examined, and all landing sites that could address them in a meaningful way were identified. Okay, so one thing I want to say, just because this is the Solar System Exploration Research Virtual Institute, that the moon really is an important place. We're not going to the moon just to study the moon. We're going to the moon to better understand our own planet and, frankly, to better understand the entire solar system. That's one of those punchlines we should all take home with us and remember to say when we talk to the public. Okay. So let's talk about concept investigation 1A, test the lunar cataclysm hypothesis. Well, the first order, you can do that by going to all basins, that is craters larger than 300 kilometers in diameter, collect those samples and return that material to Earth. Representative targeting is also something that you could implement, so you don't have to necessarily go to all of them, but you would want to go to a representative number in time and geographically to address that. Number B, determine the age of SPA to anchor the basin-forming epoch. Well, that's going to most likely be done by going to the SPA basin. Now, there is SPA ejected all over the moon, but really nail down that answer, you probably want to go to SPA or to some basin within SPA. Number C, establish a precise absolute chronology. Well, that means you actually want to look at representative craters of a variety of different ages. So you want to go to a few places that are representative of Copernican age craters, areas that give you Eratosthenian age impact events, upper Embrian age craters, lower Embrian age craters and basins, Nectarian age craters and basins, and pre-Nectarian age and basins, okay? And so you can get the sense that we generate a lot of these maps and you can stack them and you can identify places where you can do multiple investigations all in one place. Okay, the last one is assess the recent impact flux. That would involve all Copernican age craters, but that's also an issue you can do almost anywhere on the lunar surface. So that's a little bit easier one to address. Okay. Let me now jump to concept 4, which is the lunar poles or special environments that may bear witness to the volatile flux. Okay, so we have our data. There's a lot of spacecraft missions that have provided data that's relevant to this issue. One thing to point out that not all of the data gives you similar depth information, so you want to fold that into your analysis. And with that input data, the students then created a variety of products or used products that had already been developed, such as DEMs. They created slope maps. They identified the permanently shaded regions. They generated relief maps, determined maximum temperatures with diviner data, and minimum temperatures. At the time this was done, the diviner data was not public. David Page was very good to share diviner data with the students so that they could do this analysis before it went onto the PDS. It's now, of course, public. And finally, we use LROC imagery, both WAC and NAC imagery for this assessment. Okay. So there was a methodology in terms of classification of places on the lunar surface to do each of the concepts, each of the investigations within concept 4, and we generated maps, for example, with classified temperature regions where the PSRs were, maps of slope, and so on and so forth, and then used them to address each one of the investigations. Okay. So if we looked at these investigations, 4A is determine the state and distribution of polar volatiles. And on the left is a North Polar regional map, and on the right is a South Polar regional map. And all the areas in red are recommended sites for addressing this investigation. If we move on to investigation B, which is to determine the sources of polar volatiles, this is one you can actually address almost any place that you have volatiles, and so there isn't much of a descoping or filtering for this investigation. If we look at investigation 4C, which is to assess the transport, retention, alteration, and loss processes, you get a different set of recommended sites, and this is also temperature dependent, and so the students identified sites where the temperature is less than 54 K and temperatures where sites are between 90 K and 130 K. These are the two shaded green regions. And then 4D, determining the physical properties of extremely cold regolith. In this case, the regions that are mapped in blue are those that bubble up to the top. And if you actually want to know what the criteria the students use to isolate these intervals, I'll point you to the final report, which was 688 pages long. But it is available online. I have to say, it's one of the, I think it's the biggest product that LPI has generated since the basaltic volcanism of the terrestrial planets project. Okay, and then I think there is a 4E, yes. Looking at ancient solar history that might actually be sequestered in those same types of deposits. This is a less restrictive, and again, you see the recommended sites. Now, the key thing is to actually stack all of those maps and identify those common points where you could address all of 5 of those investigations, okay? And that generates a much smaller number of landing sites in red if you're up here in the front. You can see those locations. So those are the targeted places you would actually want to go if you wanted to address all 5 of the investigations. Thank you, Greg. Okay, Amundsen turned out to be at the top of the list. So here's a picture of the Amundsen Basin. You can see in red, that is the targeted area identified in the study. On the right, you can see a series of maps showing where the permanently shadowed region is, where H2O may be stable in the middle, and then at the far lower right, where CO2 may be stable. And we've actually drawn a notional traverse where a rover could lander could land in the sunlight, and then rove into the PSR, rove out, regain its power, go back in, out, back in, look at the gradients, and therefore better understand the transport processes and so on and so forth. Okay. Right, so where to begin? I want to say something very quickly. At the end of all of this, when we looked at all eight concepts, looked at all the investigations, the highest priority site was the Schrodinger Basin, which is in the South Pole Aitken Basin, and that's because we can address all of these investigations. So almost all of the investigations in the NRC report can actually be addressed within Schrodinger, okay? This is what the Schrodinger Basin looks like, and I'm going to go right past this because I'm going to show you a movie of it in a minute. But we actually have then, because that was such a prominent site, we've now done a large number of very detailed studies using half-meter resolution NAC imagery, defined traverses, defined sampling stations, defined additional station for in situ analyses, and all of that is now in the peer-reviewed literature. If you want more details about it, just let me know and I'll point you to the literature. So I know I rushed through that very quickly, but I wanted time to show this video, so Ricky or Ashkan, if you could roll the video. This is a compilation of NAC data and LOLA data to give you a picture of what the Schrodinger Basin looks like, and I want to actually talk you through some of the science that can be done here. I know for some of you in the PSD audience, you've seen this before, but we have a slightly different, broader audience with our commercial partners, and so I wanted to walk you through the same thing. So first of all, this is on the far side. I've not said that yet, so we are on the far side. The Schrodinger Basin is within the South Pole Aitken Basin. You heard all about that from Brad Jolliffe. It's a fascinating place to go to. And arguably within the Schrodinger Basin, you can find impact melt of the South Pole Aitken Basin impact event. So that is a really important reason for going there. Schrodinger Basin is the second youngest basin. It's within the oldest basin, and so potentially by going to one landing site, you can actually bracket the entire basin, forming epoch on the moon. Okay, so we're going around the rim here, the South Pole Aitken Basin, and we're going to then focus on the Schrodinger Basin in just a moment. Here it is rolling into the lower right. It is a peak ring basin. It's about 320 kilometers across. It is very similar in morphology to the Chicxulub Basin on Earth, which is related to dinosaur extinction. Okay, it is about 4.5 kilometers deep, and it has this wonderful mountainous peak ring right here that rises up to 2.5 kilometers above the basin floor. That material we've done the calculations, has come up from a depth of about 20 kilometers, and so it gives you lower crustal lithologies, and it gives you an opportunity to test the lunar magma ocean hypothesis. It also has Mare lava flows and a pyroclastic vent, and so you can collect samples of basaltic material and test ideas about the thermal evolution of the lunar interior. We're going to zoom in to the pyroclastic vent right here, which is next to this peak ring. That is our prime candidate landing site. But there are up to 6 very credible landing sites within this basin. In fact, you could send literally 6 missions to the surface of Schrodinger Basin and do completely different science in all 6 missions. This pyroclastic vent is probably the largest indigenous source of volatiles in the South Polar region. And it would allow you to determine if the distribution of volatiles in the lunar interior is the same on the far side as on the near side. There are lots of outcrops within Schrodinger Basin, so you can actually collect samples in situ in geologic context and remove a lot of the uncertainty that plagues the existing Apollo collection. Ricky, I'm going to ask you to turn that off because I know I've run over, and Greg, I apologize.
Right on. No, that's okay. Thank you very much, David. session to please come on up for Q&A. I realize we're just about 2 minutes until the end of the session, but I'm going to ask the kind permission of my workshop co-chair for just a few minutes over. Okay, all right, very good. Okay, Rick? And do we have John Gruener online as well, Ricky? Oh, there he is. Hello, John, can you hear me now? I don't think he can. So, Ricky, maybe you could relay questions to him.
He says he can.
Oh, you can? You can hear me?
We just can't hear him.
Yeah, we can't hear you. That's,
It's a long ways.
okay.
We need a communications network.
We do. Okay, all right. Tim, please take the first question.
Yeah, I have a question for David. I understand if you go to a small crater and you look at an LROC image and you see this beautiful impact melt flow, you can say that's definitely impact melt and you can date the age of the crater. For something like Schrödinger, how do you, what do you look at and what criteria do you use to say, yes, we have found SPA basin impact melt there?
Right. So one of the reasons that Schrödinger is at the highest priority is it is the second youngest basin, okay? And so if you go to the floor of Schrödinger, you are sitting on the impact melt breccias and the impact melt created by Schrödinger. There's none of the uncertainty that we face, for example, with Apollo 17. So at a minimum, you're going to make sure you definitely nail the lower end of the basin forming epoch. With regard to the SBA material that may be within Schrödinger, I mean, it did punch into what we would basically call the modification region of the SPA material. So that's where melt was ejected from the crater. We use the very same criteria that Moonrise used for detecting or determining the chemical signature of SPA material in the center of the basin. We see the same chemical signatures in the wall of Schrödinger that was punched through and exposed in the excavation process. Yeah.
Okay, please.
Yeah, so for desirable landing spots, and am I interested in is in actually desirable permanent settlements on the moon. Commercial interest and scientific interests are both going to demand someplace. Has a similar study to what you've done about scientific stuff been done for possible mineral exploitation? And if so, where would a good place to build a moon base be?
Okay, I suspect Rick and Tony will have, well, in fact, John will too, more to say about this. But the only thing I would point you to is during Constellation, there was the idea of establishing a moon base on the rim of Shackleton. And so at least during that epoch of our discussions, that was a favorite site. But at that time, the distribution of the volatiles was poorly understood. So I don't know that it has been evaluated.
Yeah, I think that's right. It hasn't been evaluated with, I think, the latest data sets in the same way David's done for the science. And there's always been this kind of push-pull problem, if you will, with having near consistent or persistent light. You know, there's no place on the moon that has permanent light, persistent light and volatiles. They don't work well with each other. So it is really a matter of understanding where that sweet spot is, and I don't think we have that answer yet. For volatiles, other minerals, elements, you know, that's a different story.
Rick, did you have a comment?
Well, we build pipelines in order to get oil and gas from places that are inclement to places where you can process them. So maybe not a pipeline on the moon, but something that allows conveyance from a rich ore deposit to a place where you can process it with in a location like Shackleton's Rim, where there's fairly long periods of sunlight. I don't know. That's not. I'm a scientist, so I can't design something like that. I can just talk about it.
Okay, next question, please.
John.
What about John?
Oh, John, yes, I'm sorry. John, do you have anything to comment? If we can hear you, that
Use
is.
sign language, John.
Yeah, we're not hearing you, unfortunately. So maybe Ricky, you could try fixing that, and in the meantime, we'll take our next question.
Yeah, so this question is for the whole panel. So my understanding is that the source of data that we have so far that's been presented, right? It's not surface data, but it's more observational, right, from orbit. And so 2 questions here. One is, it seems to me that we're in the very early stages of both scientific and prospecting. And one is, what are the major sources of errors that you see are important here? And in terms of mapping, and what do you expect to be the biggest surprises between, once you start doing surface campaign? And then secondly is, what do you see the roadmap together with industry in terms of moving from science into prospecting and, eventually settlement? So
maybe I'll start with an Apollo thing and then let these gentlemen take the volatile part of that, okay? Sure. So what you say is not quite right in terms of the bedrock geology or the rocky components. Based on some of the rocks that Jack Schmidt and his colleagues collected, we have a pretty good understanding of what the regolith is like, what the soil is, the finest grained soil on top of that is like, and we also understand how messy impact cratering processes on the lunar surface have made the geology. Okay, so based on that, we do kind of understand what it is we want to analyze, what we need to analyze, and we better understand that if we are going to really make some big progress on some of the geological issues, we want to go to places where the geologic context is accessible. And so that is why someplace like Schrödinger Basin is very attractive from a geology point of view, why Orientale, Antoniadi are very attractive places to go for geology. The answer for volatiles is different, and there are better. I'll let Tony and Rick address that.
I guess just to be clear, can we even talk about the statistical significance of data from the information that we have so far? So I would be really, really curious to hear your perspective on that.
Okay, I'm not sure I understand what you mean by statistical, but so let's just take Schrödinger. We know that peak ring has a north acidic rocks and olivine-bearing, possibly troctolitic rocks based on the M-cubed spectral data from orbit. I can't tell you in detail what the compositions of the minerals will be in those lithologies, but I do know that they are probably intrusive magmatic rocks from the lower to the mid-crust to the moon. And if we go and collect those samples, we're going to answer lots of questions related to those types of rocks. So there's really no uncertainty, statistical uncertainty on the types of questions that we'll be able to answer if we get those samples.
Okay. Tony?
Sure. For the poles, it's different. We haven't landed at the poles. So the poles are a little bit terra incognita right now in terms of what is going on at the surface. And I could point to innumerable questions we have right now. I mentioned earlier in my talk that the poles don't make a lot of sense in terms of distributions of water. Where it's cold enough to have water, you don't always have water. Some places you have surface water, but you don't see the neutrons. You see surface reflectance of water signatures, but you don't necessarily see it in the neutron counts. Now, there's lots of resolution issues and things like that, but it looks statistically sound that there's something going on we don't fully understand. Unlike Mercury, where typically, where it's cold enough, you either see the water and the hydrogen from the neutrons, or you see a leftover lag that looks like it was something from a desiccated water layer. From a planning point of view, though, what's interesting is what we've discovered is when you start looking and digging into the data, I think Tim mentioned earlier, there's so much to gain from higher resolution data sets. And that's what we've really been trying to achieve. I mentioned at the end is working at these scales that as you work and plan a rover mission, in particular on the lunar surface, you really want to understand. LOLA data is fantastic, and down at the poles it's dense. You have 10-meter spacing. However, often there's averaging portions within that data that are 100 meters across. It's an orbital thing. And that's bad because you can be totally misled. So that's where the stereo imagery and the photogrammetry overlaid with the LOLA we've had to work with that to fill in those gaps because they were so onerous to our planning. We couldn't do it otherwise. That's where commercial entities can really step in with processing tools to look at the data in new ways and to refine it, really make it much more usable. The last thing is just understanding the impact of small changes in terrain, the uncertainties in the LOLA data with altitude. That's important to understanding where the Earth is. When you're trying to point to the Earth at the poles, a degree or two matters because you only have a degree or two. So actually, even just the little small uncertainties, beating those down, understanding those, how to mount, that's something we can all work on with the current data set. Yeah.
Thanks, Tony. Rick, you had a point?
I have a question for you. What are you talking about? What data set are you talking about asking for uncertainties for? Because they're all different and they all have different uncertainties. So which one are you referring to?
Sure, and I realize it's a really broad question, but I was just trying to get to and I know you talked about landing sites, for example, and I'm sure there's different sources of errors in the landing site. So I guess I just wanted to get the gist of sources of uncertainties, confidence in terms of the data, across the different subjects that you're covering here. So,
well,
yeah.
we rely on the neutron data sets to tell us where the hydrogen is most concentrated. But unfortunately, those are the lowest resolution in spatial resolution data sets. And so they're smeared out. You can think of them as poor glasses that don't let you see sharply. Whereas other data sets like LOLA or LROC are very, very high resolution data sets. So those things together, I mean, people like David and his team have put these things together to try to get an idea of where you're most likely to find something of interest for resources, for example.
Well, okay, so you just said most likely, right? So can you put the quantification on most likely, right? So
just where the hydrogen and all the other parameters maximize and come together. So it's the Venn diagram all fitting together in the right way.
Thank you. We should move on to the other questions. Just the three people that are in line now, and then we're going to need to move on. So Jack, please.
This is more of a suggestion that as we talk about the bombardment history that the moon can define for us for the inner solar system, I think we should mention much more specifically that that's the Hadean on Earth. And that, first of all, it broadly defines the Hadean. And that was a time when complex molecules at least were forming. And secondly, if that history is episodic in terms of the formation of these basins, it gets much more specific with respect to what was going on in the Hadean and can help us define the boundaries in the Hadean on Earth. I mean, so that's one reason why it's so fundamental and at the top of all the lists is it relates directly back to the Earth's history and to the history of at least the formation of complex molecules here on this planet. So I just suggest that we keep that a little bit more in front of us rather than just saying it's the bombardment history of the moon.
Yeah, no, Jack, you're absolutely right. In fact, in many other contexts, we link it to the discussion of the origin of life. And in fact, soon after the president's vision in Bush led to Constellation was delivered, many astrobiologists I was on a panel were asked to address what the scientific outcomes of going back to the moon would be. And there is an NRC report that parallels the 2007 one that I've been mentioning that puts the impact bombardment at the top of the list from an astrobiology point of view for the very reasons you just identified.
And Dave, I just would argue and knit with you a little bit about Apollo 17 not knowing the geological context of samples. Okay?
And for those of you who know me, I was baiting Jack just a little bit.
This was clear. Okay. Okay. All right. Carly, please.
Okay. I have a concern I'd like to come back to. This has been a wonderful discussion we've had today with a lot of different panels. Very exciting, lots of opportunities from different parts of the community, really rich and exciting to see. I was stimulated by some of the things that Rick mentioned, but I'd like to hear people's overall comments.
Uh-oh, stimulated from Carly.
Well, when you're talking about different levels of exploration, from simple to medium to more complex, and the kinds of instruments that can be included and should be included, you know, 60 years ago, we only had to have a really nice image and some beautiful samples, and people would say, wow. Now people are or in particular the current generation, are used to virtual reality and three-dimensional imaging and real-time sequences. These require very high bandwidth to return. And that was only mentioned once or twice during the discussion today, and it really worries me because, yes, not all instruments need a high bandwidth, but people expect it. And you know, if we don't deliver it, we're going to look irrelevant. So if anyone wants to comment on that, or maybe this is just something to be thinking about as we move forward.
Yeah, Carly knows another context. I've actually raised this issue multiple times, and we've done some calculations that indicate we need, you know, at least a megabit per second data rates. And our astrophysical colleagues who want to put a radio telescope on the far side are asking for 3-4 gigabytes per second data rates. And so these are things that we need to be aware. I mean, we need a comm relay that can deliver that, can take data from the surface to the far side, cislunar space, and get it back to Earth. And we have to have the assets on the Earth to receive it.
But that's several steps down the line, not the first or second step.
Fair enough. Right.
Well, I mean, I've articulated we should have a comm satellite up now, next year, or 24 months from now. And I don't understand, we have 2,000 comm satellites in North orbit. I do not understand why we cannot have a single comm satellite in cislunar space.
Okay, any other questions?
We found one for Apollo 17. They just didn't want to fly it. There were two Tyros on the shelf, and we figured out a way to launch it within a year and get 2 satellites in that place for redundancy.
And for that reason...
Now, whether they still exist or any other ComSat still exist, I don't know.
And for that reason, Jack didn't get to land on the far side like he wanted, and he had to put up with Taurus Littrow Valley.
Yeah. John, I don't know if you can hear us, and we can hear you now. I got a thumbs up from back there. I don't know if you have any comment on this as well? Did you look at this in Constellation, and are you looking at it now? Okay, apparently our comlink is down there too. Maybe that's the comlink we need.
We can't even do this on the Earth?
No.
Apparently, yeah.
Solve it on the Earth first.
So one thing I can add, though, Carly, is for RP, that's definitely been a forefront. There's no measurement requirement for that, but at the highest level in AES, they've understood that that is a need. The expectations of the public is that you're going to have HD television video coming from the surface of the moon, and there's other aspects to it. Right now, the data link for RP is a necessary data link is 230 kilobits per second. That said, you can do a lot with that, especially if the rover is stationary and not needing navigation camera images. Right. The one way we plan on engaging right now the community is to have this real time. The operational software is a web-based software that you can have on your phone, on your iPad, and it will be streaming the data as we see it. You can't actually control the rover. There's a different control system for that. But you can pull up your iPhone, see what the rover's doing, see the images coming down real time, and it's actually, you can self-manipulate it. It's called Warp, very cool stuff. You can design your own displays. You can look at telemetry and things like that. That's one avenue we're pursuing as a way to better engage a community that demands some immediate insight into what's going on.
Hey, Tony, I'm watching our mission operations manager right back there, Jay Trimble.
Did I misspeak, Jay?
No, he hasn't fallen over.
Yeah,
and
he
Tony,
would throw something at me if I did.
I want to say HD video is so 2010.
I know.
But look at what's coming out of CES
4K,
this week, and it's 8K actually.
8K now?
8K, yeah. So Clive, you have the last question.
Oh, lucky me. Well, I'll be brief because I'm going to follow up on what Carly was saying. We're starting to see now an enabling capability that has commercial opportunity written all over it, which is a very capable communications network that can be both, it can be international in scope, and it can be leveraged because it will not only enable RP and other US missions, but also international missions, as well as private missions to the far side. And it seems that the political will needs to be there to actually do it. And I think that, you know, one of the things that comes out of this meeting is a very strong voice that, you know, a communications relay or a network around the moon becomes enabling in so many ways, not only for science but for exploration and achieving that permanent presence that we would like to see. So that's number one. Number two, I love resource prospector. But when are you going to become a real mission in terms of what's this Class D crap when you're going to the lunar surface with a solar-powered rover? We had a finding from the League meeting, and we haven't heard anything back on that finding, about accelerating the progress for RP. It's becoming highly relevant now, and I know you guys are ready to go, but it keeps on slipping. There's commercial opportunity there to get this to the moon. Has that been
I'm
explored?
just a lowly scientist working on the project.
Yeah.
Man. I don't know if Dan's
No
in the
comprendo.
audience.
Can't say
If I was Dan Andrews,
over
the
there.
project manager.
You want to come to the mic?
Yeah,
Dan?
Dan, I can take it, but then you'll beat me up later.
Can you go to the mic, Dan? If
Hey,
Jeff's gonna do-
Oh,
So we've heard a couple of presentations ago about the Jason Kruzan at the hearing, the science subcommittee hearing, I think it was, talking about some procurements that are going to be coming out this year. We're working statements of work and things like that. So I think it really is moving in that direction, but I feel you.
no, because it was supposed to have launched in 2017.
Yeah.
Just, when it was first proposed, and here we are, 2022. What's
It's
going on,
actually-
people? Is this just a PowerPoint display, or are we actually
Yeah.
going to do it?
It's far more than PowerPoint.
I
we did a
realize that, but
presentation to our friends here. And
The frustration that comes from the lunar community in terms of we have a very capable mission that could be more capable if it was allowed to be more than a Class D. It could be very enabling. It can also be a way to actually cement, I'll put my US hat on now, US leadership in exploring the lunar poles. And, you know, it seems to be that there needs to be a push to actually make it happen.
Well, one thing I can say, and I've got the two PSD leads right in front of me here, is we have been talking even more than ever. We always have been, but the engagement between AES and SMD, PSD in particular, has been accelerated. Mm-hmm. And I think that's in the direction you're talking is a good direction to go. Yeah, we all feel your pain. We've been ready to go, and for a number of reasons, most of which aren't technical, we haven't been able to get off the block yet.
Yeah, understood, and I
the-
apologize for being politically incorrect, but
No,
I put it
that's
down
your
to lack
job.
of sleep.
okay.
The reality
Are-
is that this project has been leading where the U.S. has been focusing its attention for some time,
Yep.
meaning way in advance of. And so now with some of the recent decisions that are out there, it's time.
Yep.
So.
Okay, thank you.
All right. Thank you very much. Thanks again to our panel. Thank you, John, if you can hear me. So, great. And Clive, are you going to turn it over to my co-chair right now to introduce